In the early 1900s, the Rutherford-Bohr atomic model was the most commonly used one by the scientific community. However, it has some limitations. For example, it does not explain how protons in the nucleus can remain so close to each other despite the repulsive forces between these positively charged particles. In 1932, the English physicist James Chadwick finds the answer by discovering a new particle in the nucleus, the neutron. This particle is neutral. Neutrons form bonds with protons and decrease the repulsive forces between them. Neutrons make the nucleus stable. The Rutherford-Bohr atomic model is replaced by a new model, the simplified atomic model. The difference between the Rutherford-Bohr model and the new simplified atomic model is the presence of neutrons in the nucleus. Let's represent the chlorine atom, for example. First, we identify the element in the periodic table. The atomic number of the element corresponds to its number of protons. Chlorine has 17 protons. We draw a circle representing the nucleus of the atom with 17p plus written inside. Now let's determine the number of neutrons. The relative atomic mass is essentially the sum of the number of protons and neutrons, which are the heaviest subatomic particles. To find the number of neutrons, we can simply subtract the atomic number or the number of protons from the relative atomic mass rounded to the nearest integer. The relative atomic mass of chlorine is 35. By subtracting 17 protons from it, we obtain 18 neutrons. We indicate the neutrons in the nucleus by writing 18N0. The next step is to represent the electrons. In a neutral atom, the number of electrons is equal to the number of protons. Therefore, chlorine has 17 electrons. To distribute the electrons, we begin by filling the electron shells closest to the nucleus. The first electron shell can contain a maximum of 2 electrons. Let's draw them on either side of the nucleus. There are 15 electrons left. The second electron shell can contain a maximum of 8 electrons. Let's draw 8 electrons on this shell. We are left with 7 electrons. Since the third shell can hold a maximum of 8 electrons, we can distribute the last 7 electrons there. The electron configuration of chlorine is now complete. We also could have used the elements period and group to distribute the electrons. The period indicates the number of electron shells, and the group indicates the number of valence electrons. Chlorine is in the third period. It means that it has 3 electron shells. It is also in group 7. Therefore, it has 7 valence electrons, which are located on the last electron shell. The remaining 10 electrons can be distributed between the first and the second shells. The simplified atomic model can be represented in short form. Start by drawing the nucleus with the number of protons and neutrons indicated inside, like before. Add arcs to the right to represent the electron shells. The number of electrons on each electron shell is written under the corresponding arc. An E- is added to denote the electrons. Even though this model is more complex than the previous ones, it is now called the simplified atomic model to differentiate it from the more complex representations that researchers have been developing more recently.